Now we're going to talk about heat transfer in weather systems. And in addition to the heat that you can feel through conduction, convection, and radiation, we're going to talk about latent heat of evaporation. Latent heat is the energy that's involved in heat transfer when the temperature remains the same, for example, when water is boiling or condensing, or when water is freezing or melting. Latent heat examples can come from, for example, an electric kettle on the stove or on electricity that moves water boiling from liquid water to water vapor. And in this case, it's still at 100 degrees Celsius, but the water you're adding energy, latent heat of evaporation, to move the phase from liquid to gas. That energy comes back when you stick your hand in the steam, in the water vapor. It condenses on your hand and it burns you because so much energy from the latent heat of condensation of that water gets into your hand. In addition, we can cool ourselves by latent heat of evaporation. When the water evaporates, it actually cools, takes the energy out of our warm blood and cools us. And you can cool a warm drink in an ice cooler by melting ice and that latent heat of evaporation, which is quite a lot. That actual latent heat of evaporation will take, or melting, take that ice as it melts and take all that heat out of the drink and make it cool. So much cooler than if you just had liquid water in there. And in storms, rain, when it rains, we move from liquid gas water to water liquid, and that latent heat of condensation is stuck back into the storm, and it actually helps power a thunderstorm as it goes. So this is a Sling psychrometer. It's a way to measure humidity in the air, and it has a dry thermometer and a wet thermometer. The dry thermometer just tells the temperature of what it is, and this reads 85 degrees. And what I'm going to do is take the wet bulb and dip the bulb that's covered in a cloth in water, and I'm going to sling it around so that when this happens, the water evaporates from the bulb, and the evaporation from liquid water to water vapor takes latent heat of evaporation out of the thermometer, and the thermometer then gets cooler. It appears cooler. And the difference between the wet bulb and the dry bulb will tell us the humidity of the air. So the wet bulb is 75 degrees. I can take 75 degrees wet bulb, 85 degrees dry bulb. I can put on my little ruler here 75, match it up with 85, and then I can read off the little magic thing. It says that it's 65% humidity. And so what happens is, if it's 100% humidity, the wet bulb and the dry bulb, the wet bulb won't evaporate at all. It's 100% humidity. So the temperatures would be the same. But if it's 0% humidity, the wet bulb will evaporate very fast to the dry air, and there'd be a dramatic change between the wet bulb and the dry bulb. This is somewhere in between 65% humidity, because I had a 10-degree difference between 75 and 85 degrees. So the Sling psychrometer compared the wet bulb with the dry bulb, and it is a measure of the humidity, in that there's a demonstration of the fact that latent heat of evaporation can really cool the object or the system or the body or the animal from which it's evaporating. And the humidity stops that evaporation or slows it down. And so when they say it's not the heat, it's the humidity, it actually is both. It's both the heat, but as well as the adaptation of the human body or the animal, which is trying to cool itself by latent heat of evaporation, but it's not able to if it's too humid. If it's 100% humidity, you have no evaporation, and that's called the heat index when you combine this heat with the humidity. So there are a handout of 20 heat transfer scenarios that is available on the website, and they are ordered where the simpler ones are at the top and the more challenging ones are at the bottom, and you can sort of move around and pick the ones that are interesting to you. And and you can share some of these heat transfer scenarios with your mentees, or talk about them, or you can make some up yourself. But I'm going to go over a few of these. The first one, how is it that our hands are cold but not the rest of our bodies? And we know something about conduction, right? The surface area matters. So the surface to volume ratio of your hands is much more than your stomach or your abdomen, and so we're losing heat over a larger surface area. Clothing matters. So the thickness, or if you insulate the distance between the warm skin of your hands and the cold air, we normally wear clothes around our abdomen, a shirt, a jacket, and so that limits the cooling of your warm body. But over your hands, if they're exposed, you're cooling right directly to the cold air. But of course, you can put gloves on and eliminate some of that by, again, insulation and increasing the thickness or the distance between the cold and the warm. And the other thing is that we have internal core temperatures that can be far away from the skin where the cold air is being in contact with. And the hands are not so thick, and so it's always quite close to be able to lose the heat from the warm blood to the cold air. Number 5 is how does a swan, you might have seen this at times, how does a swan stand on a frozen lake and not get frozen? And so you might see a swan sitting on standing on one foot, and of course 1 foot it eliminates half of the heat loss that you would have if you stood on 2 feet. So the area is reduced. The difference between the foot and the ice is not the same as the difference between the body of the swan and the foot. And so they have this very special circulation system where the temperature of the leg is actually colder than the temperature of the body. And then that has a third circulation with the foot, and the temperature of the foot is actually quite close to the temperature of the ice. So that delta T, or the temperature difference between the foot and the frozen lake, is not so much, and therefore we know is less of a heat loss. There's a question about Bedouins living in the desert wearing black or white robes. Which one do you think is cooler, and why do they wear what they wear? And you would think, because we know about radiation being absorbed more by black things, that the black robe would be hotter. And that is true, but what also is true in this sort of complex system is that the black robe is hot on top, but if it's loose, it allows the cool air to enter from the bottom and increase the convection. And we know convection is a very efficient way of heat transfer. And so if we have a loose robe that allows cooler air to flow faster because we've got a hotter top of the robe, the black robe actually has more cooling than the white robe and feels more comfortable. So the Bedouins actually wear black robes, black loose-fitting robes, and it actually keeps them cooler. So we have to combine radiation with convection and conduction to be able to understand the system. Number 19, why does it feel cold when you get out of a pool, even on a very warm 90-degree day? So what we know about this is that latent heat of evaporation is an efficient way of cooling, even in warm weather. So the water evaporates from your skin, taking the heat out of your body and cooling you to make you feel even cold. You might even be shivering on a 90-degree day. If it's windy, you get even colder because the evaporation is faster and that latent heat of evaporation is lost from your body. But if you don't want to feel cool, just eliminate the evaporation process. Use a towel to dry off that water. You don't even have to wrap yourself in the towel. Just remove the water so the evaporation stops, and you eliminate most of the cooling, which is the latent heat of evaporation. In addition, this might not be recommended, but if you were to make the air near your skin at 100% humidity, then you would have no evaporation either. You can still be wet, but it wouldn't evaporate. And if you cover yourself or wear a plastic something, poncho, that would eliminate the evaporation and keep you warm as well. So there are a number of adaptations about and applications of heat transfer in sort of real systems. It also applies very much to weather systems, the formation of weather systems, and the dissipation of weather systems. Thunderstorms, convective heat transfer, warm air rising very close to cool air sinking. This differential heating by the sun causes thunderstorms, and the warm and the cold air moving convectively next to each other is what causes lightning and thunder. If you have a sustained release of the latent heat of precipitation, that actually feeds the air rising more energy into the thunderstorm, more convective overturn, and it actually intensifies thunderstorms. Heat waves are when radiation comes from the sun and the air just doesn't move. There's no way to convectively cool the area, and the heat builds up. And some of the adaptations of that is you could adapt by cooling yourself, the evaporative cooling, or you could do something with your home in terms of reducing the amount of absorption of the radiation, like having a white roof is much better than a black roof, for example. Hurricanes are absorbing heat from a warm ocean water at 80 degrees Fahrenheit or above, and that's what feeds the energy. So when a hurricane travels over land, there's no more source of energy, and eventually the hurricane dies out. It also dissipates through losing energy from friction and dissipation through convection and movement of the winds of the storm over a larger area, and so the energy density goes down. If you have warm ocean water, more of the ocean at warmer than 80 degrees and warmer even than just 80, 83, 85, 87 degrees, you're going to have more energy into each of the hurricanes, and the intensity of the hurricane is going to increase. And if you have more area of 80-degree water, you're going to have a higher frequency of hurricanes forming. So the challenge question, what can you and your family do to keep cool in a heat wave or keep warm in a blizzard? We can apply all of these heat transfer things that we've learned over the last two videos. Conduction, how do you eliminate the cooling if you want to stay warm? And we know about the area and the temperature difference and insulation, whether that's cooling to the ground or to the air. Convection, we can make some adaptations to where we live, either with our clothing that we wear, with loose-fitting or tight-fitting clothing in terms of the Bedouins, for example, or the house itself. Can we cool or warm the house due to convection, fans movement, radiators moving air around? Or do we want to eliminate the convection cooling so that we can keep the heat trapped somewhere? Radiation, we can understand and adapt our behavior depending on, do we walk on things that are black or things that are white? Well, it's much cooler and easier to walk on things that are white. Do we trap the radiation when it converts from visible to infrared radiation? Radiation is really the source of all weather energy, and understanding sort of how these weather systems start can help our adaptations to the weather systems as they impact us. Very important is this latent heat of precipitation or evaporation. It causes thunderstorms to intensify, but when we adapt to these storms, how do we eliminate evaporative cooling if we want to stay warm? How do we stay cool by evaporative cooling during heat waves and moving winds across our body so that we conduct more heat away into the air? So be creative. Think about the fundamental learnings about conductivity, convection, radiation, latent heat of evaporation as we think about these adaptations for you and your family to adapt to different weather situations.